14, still in week 4. So our lesson objectives here are to define fatigue and specify the conditions under which it occurs. From a fatigue plot for some material, determine the fatigue lifetime at a specified stress level. And B, the fatigue strength at a specified number of cycles. We're going to define creep and specify conditions under which it occurs. And given a creep plot for some material, we're going to determine the steady state creep rate and the rupture lifetime. And we're going to get into the lesson, but first, movie time. Not blackboard time, movie time.
No danger, of course, once we're in the air.
Well, that's okay. If you keep a man standing by the lever here on both taking off and landing, so nobody catches the coat or anything.
Right, I'll see to that. What are you doing here?
Captain, I just have to...
Well, now that you're here, I want you to listen. I've told the inspector here all that you told me. Now, if you've anything to add, I want to hear it now, and I want him to hear it.
No, sir, I don't have anything to add.
As London apparently doesn't take her opinion sufficiently seriously to order this aircraft grounded, I'm flying around to Montreal, and I want you to get off and stay off.
Well, Captain, you mustn't take off in this airplane. You can't do it. Believe me, mathematics is a very exact science.
Explained that already, Mr.
Captain, it'll be just like the one in Labrador. The stewardess, all these people.
Now, for the last time,
Captain,
Mr. Hammond.
Leave that alone, you fool! Got the plow!
Okay, so this is the movie No Highway in the Sky from 1951. And the only reason I know that this movie exists is because my father is a huge movie buff, and every Saturday morning was black and white movies all the time. And one time I was actually in college at the time, but I happened to be home, and I was having coffee and sitting there, and Dad was watching a movie. And I realized that one of the movies that he was watching had a direct parallel to something that I was learning in class. And that is this movie. So my question here is, what would drive this man to destroy an aircraft by lowering the landing gear while it was landed? Is he insane? Well, maybe a little bit. But he also said the terminology mathematics is a very exact science. And also, he mentioned that the possibility that there's a whole bunch of people in danger on this plane. So something that he knew that nobody else on this aircraft knew about drove him to destroy the aircraft so it couldn't fly any longer. Well, that's what we're going to talk about today, and that is going to be fatigue failure. So here we are, fatigue failure. Fatigue is failure under a lengthy period of repeated stress or strain cycling. Okay, so you take something and you put it under load, and then you let off the load. And then you put it on again, and you let it off again. And you just keep going like that, and then eventually the item will break, okay? Is this strain hardening? Is that what's happening here? No, it's not strain hardening. Is it surpassing its yield stress every single time? And because of that, because you're deforming it every single time you push and pull on it, is that why it's failing? No, it's not because you're surpassing yield stress. This is an interesting type of failure. It occurs over a very long period of time, and it has to do with the motion of defects in a material at stresses that are even below your yield stress. Okay, so stress varies with time in fatigue failure or in stress cycling. The key parameters to note here are your stress amplitude, S, your maximum stress, sigma m, or rather that might be mean stress, my bad, that's mean stress, and cycling frequency, okay? So some key points. So fatigue can cause part failure even though our applied stress, sigma maximum, is much lower in some cases than our yield stress. And this is responsible for 90% of mechanical engineering failures, which is pretty crazy. This is just a schematic diagram of an apparatus that would actually perform this kind of testing to actually induce fatigue failure on something. So you have a load that's put on a little, so these are weights that are put onto this little, not a pendulum, but hanging weight. And then that's applied to two different sides of the specimen. And as this motor rotates this flexible coupling, it will move the system up and down continuously until finally this thing will break. Okay, so that's how you are applying some stresses on this. So it's kind of an interesting design. We're going to see another design actually later on, and I'll show you how you don't have to use this kind of setup. You can use a lot of different setups. Basically, anything that you can apply a force and release the force with over a long period of time will instigate fatigue failure. So I am going to be writing on the board a little bit this lecture. This is actually the only board that I have for this lecture. So we're going to start with cyclic stresses. Okay. And basically, when we're trying to induce fatigue failure, or when a fatigue failure occurs, what's going on is, let's say this is my my stress axis, and then we're going to draw the 0 mark right here. Okay. And what's happening is stress is being applied kind of like this. So we're going to start out with a sine wave pattern. And this position would be sigma max. Sigma m, which is our mean stress. Sigma m is going to be equal to sigma max plus sigma min divided by 2. So that would be this line here, with this position being sigma min. We have a range to keep in mind. So the distance between this position and this position would be sigma r, which is just equal to sigma max minus sigma min. And then finally we have the amplitude. And the amplitude, S, will just equal sigma A, which is equal to our sigma r over 2. Another way to write this is just sigma max minus sigma min divided by 2. Okay? So in this case, if your stress is about 0, then your if stress is about 0, then your range, your stress amplitude will be equivalent to your mean stress, okay? But this doesn't necessarily have to be the case. What could happen is, imagine for a moment that 0 is actually down here, and this is like 40 megapascals or something, right? Then, in this case, sigma m is not equal to sigma A, okay? Or S. Okay? So that's just what we're talking about when we talk about our different kind of features here. And then obviously the distance between this point and this point would be your frequency f, right? And that can have an effect as well. It not necessarily so much for our calculations, but it will have an effect for vibrations, because if your frequency of loading is close to the harmonic frequency of the object that you're looking at, it can cause it to actually increase the amplitude of vibration over time, and that can cause failure. So, like outright failure, not just fatigue failure. But fatigue failure is just the straight loading pattern, and we'll call this point up here sigma y. Okay, so we're well below our yield stress, right? Maximum doesn't even get too close to sigma y, and yet at this stress, we're saying that fatigue failure can occur. So it's something you have to keep in mind when you're designing things. Okay, so types of fatigue behavior. So we have a case for steel and a case for aluminum, okay? Essentially what we're looking at is stress amplitude plotted over the number of cycles that the material has gone through, okay? Look at the magnitude of number of cycles. 10 to the 3, 10 to the 5, 10 to the 7, 10 to the 9. This is a log scale. And as you can see, this is a lot of cycles. I mean, we're talking potentially billions of cycles here, right? Well, what we find is that if our stress amplitude is above a certain position, then as we cycle this thing, we will cross right into an unsafe region that's marked by the red line, okay? If we cross from our safe region into the unsafe region, we're going to break, right, from fatigue failure. However, for steel, there's actually a zone below which we will always be safe, okay? So you can actually cycle it as many times as possible, I mean, up to infinity, and it will never fail through fatigue, which is nice, because, you know, that's something really nice about steel. But if you're anywhere above this limit of fatigue stress amplitude, then you will have fatigue failure. But in this case for aluminum, this curve continues to drop, and it will just keep dropping, okay? So aluminum actually does not have a fatigue failure limit, okay? An amplitude at which fatigue failure will not occur, okay? That's what I'm saying here. For some materials, there is no fatigue limit, okay? And then our fatigue life is just the total number of stress cycles to cause fatigue failure at a specified stress amplitude, okay? So if I say I'm going to sit up here at my stress amplitude at this position, and I draw a line all the way over to the right, and I hit, let's say, 10 to the 5, then 10 to the 5 cycles is all that my part will take before it fails, okay? So that's something important to keep in mind. And then obviously if we increase that amplitude, we get more, we have less cycles before failure occurs, okay? And then obviously this can go all the way up, stress amplitude can go all the way up till near your yield stress. Of course, maximum can't go above yield stress, or else we're not still really in a fatigue failure mode. Then we're in like a strain hardening mode, right? And fatigue will occur much faster. Okay. Now, you might have heard something about like car manufacturers in the automotive industry talking about things such as design for failure. Well, automakers will never admit it, but people around the automotive industry will talk about it. And it's this idea that theoretically, if we can actually calculate the number of cycles to failure for a specific part, like this is a very part-dependent graph, right? If we can find the number of cycles to failure, we can design our system such that after a predetermined set of time, it will fail, right? We make that material thin enough, which makes our whole assembly cheaper to make, right? Because we're using less material. Then we can actually design it to fail at, let's say, 10 years, or let's actually say 4 years. We'll say after 4. Nah, that would be too low. That would be way too low. We'll design it to fail after 10 years. Okay, 10 years, you get a loan on a car, and after 10 years, you have finally paid off your loan, but your car dies, right? Because something inside has failed that's critical, right? Then you need to go back to the manufacturer and buy a new car and get a new loan, right? So it's this idea of if they can just keep you buying more loans, that's a steady rate of income. And that kind of thinking can be made when you're talking about fatigue failure, right? That I would consider that unethical behavior, to be honest with you. I think as engineers, it's our job to design things for continuous use. Now, that's not necessarily the case for every single part you might ever make. It might be necessary for it to break after a certain period of time to prevent some kind of dangerous eventuality. But bringing that kind of money-making aspect into it and saying, well, we want to keep people in debt buying cars over and over again, I would consider that unethical, but others might have a different view of that. Okay, so we now know what fatigue failure is, so back to the movie.
Now, mind ahead, sir.
Find it, Meg?
Yep. Fuses keep blowing on the undercarriage safety circuit.
Here we have the radar screen, sir. Radio altimeter, radio compass, DF loop,
Excuse me.
DRC repeater, which is duplicated on the pilot's panel just in case.
Oh, yes. Well, I don't suppose many things go wrong these days.
Almost never. We only use reconditioned engines on this line. We get new ones every 600 hours. They're pretty things.
Oh, they're really obsolete, though.
They're good enough for me. Now, the cylinders missed to take yet. This is the third set. Have me out of a job if they don't kick up a little something soon.
Oh, well, I wouldn't think that would happen. Did you say the third set?
That's right.
But I thought the reindeers were new on this run.
They are on this run. But this was one of the first two built, and the builders wanted some experience with the ship before turning the fleet over to this line. So we were loaned out for a while on the South American run.
Well, for how long?
Quite a while.
Well, could you tell me exactly how many hours this airplane has flown?
Certainly. It's right here. 1,422 up to takeoff. Anything else, sir?
No,
We have dual ADF indicators.
Okay, so what's going on here? Well, this guy, played by Jimmy Stewart, is actually an engineer, and he works in a laboratory, and he's investigating this new thing that can actually cause airplanes to fall out of the sky for no apparent reason. The tail of the aircraft keeps falling off of the specific design of plane, and nobody really knows why. We'll continue a little bit with the movie.
Well, did you learn all about airplanes?
Mr. Dodson, I must speak to the captain at once.
Captain Sanderson is very busy, Mr. Honey. If there's something I can do,
Mr. Dodson, please tell the captain I have every reason to believe this airplane's in very serious danger, and I insist on speaking to him, please.
I'll see what I can do.
Well, Mr. Honey, what's all this about? I understand you're not very happy about something.
Captain, this airplane and everybody in it is in very serious danger, and you must turn back at once.
What sort of danger?
Captain, I've been working on a theory on nuclear fission. I used the tailplane of a reindeer as a basis. According to my calculations, it'll fail in 1,440 hours. Now,
I see, but now this is a theory.
Now, I assure you I've done a great deal of work on this, Captain. This airplane has flown 1,422 hours as of takeoff. The tailplane can fail at any moment.
Mr. Honey, I don't believe you realize the very strict procedures under which an airline operates. But have you ever heard of an airworthiness certificate?
So essentially, this the captain of the airplane, he's not going to do anything about what this engineer is talking about. He's never heard of anything called fatigue failure. Of course, they haven't even termed it this. In fact, he mentioned something called he mentioned that it was based on a theory of nuclear fusion, which is really funny. But it's the idea that back in these days, they didn't really know anything about fatigue or why it occurred, because a lot of the advances that have been made in material science have really been since World War II. And this movie was 1951, so we're really on the tail end. I mean, this movie came out 6 years after the end of World War II, right? And so fatigue failure was not a very well-known concept back in these days. And so none of the pilots have any idea what he's talking about, and most other, aircraft manufacturers have no idea what he's talking about. And yet these airplanes are falling out of the sky. And he's worked it out, and he said that after 1,422 hours, these planes should fail, right? And how can he do that? Well, he can come in and he can say, well, I know that this one wave is a cycle. That's what we call one cycle. I know what the frequency of that is, which is the amount of time it takes to go through one cycle. This could be anywhere from 50 milliseconds to a second, right, depending on how wide your frequency is. And he's worked it out in terms of number of cycles. How many times does it cycle in the air? Now, again, that's another thing I haven't mentioned, but when the plane's flying through the air, the tail here in this case, but also the wings and other things, are vibrating because of wind flutter. Okay, that's another thing that has been improved on in modern aircraft. There's a lot less flutter, and so a lot less of this happens, but this still does happen when you're flying through the air. If you want to see that, when you're driving in a car and you stick your hand out the window, you can, and just tilt it up or down, you can actually feel a little bit of that flutter. Okay, especially if you orient your fingers and whatever in a certain way. Okay, so that's what he's worked out. And what he has found is that these planes are operating at an unsafe stress amplitude, and that over a long enough period of time, after a certain number of cycles, they will hit failure. And he's worked out the number of cycles, or how long it takes each cycle to go through, and that total time of flight to failure is 1,422 hours. To me, for this to be in a movie is amazing and unbelievable, and I wish that we had movies like this today. And so, of course, if we're going to watch a movie, we got to see the end of it.
Yes, and he'll probably do it, too. We'd better go down and see him
Your
before he...
secretary sent this over, Sir John. She tried to get hold of you at the meeting, but they wouldn't put her through. She said it was very urgent.
Oh, thank you.
Where is Sir David Moon? I hope he hasn't left. I can't wait for this. It's from Nixon in Labrador. He says they found the tail spar, and it's a fatigue fracture if ever he saw one.
Sir John, I've had the most incredible piece of information.
You haven't heard mine.
They've just made the first test flight on our plane at Gander after it was repaired. It made a perfect landing on the airport, and the tail collapsed while it was taxiing to the hangar. I could hardly believe it. And I
this to help you.
Mr. Honey, we've received 2 messages from Labrador and Gander which bear you out completely.
Oh, well, that's good. You know, I can't see where I could have gone wrong in this. I've worked it out through 3 different channels.
Didn't you hear me? I said...
Temperature, that's it. That's a variable factor, isn't it? That plane in Gander had been flying in the tropics. This test is in a heated shed. It would have collapsed on schedule if I'd lowered the temperature 40 degrees.
And so, the the actual reality of what he's looking into bears out well compared to what he's telling everybody is actually happening, right? It's hard to see in this. I'd like to rewind a little bit to see, rewind, to see if we can actually see a little bit of his test setup. This is actually a really realistic, I mean, they probably went to an actual material science testing center, like an actual lab, to run, to shoot this movie. Because this is a highly realistic looking laboratory for the day. And let's see if we can catch the actual setup. Aha, yes, here it is. Okay, so you have a control station here, and this control, actually 2 control stations, and you have knobs and dials and indicators, and these are connected to I mean, this has to be like, a movie director would not be able to like come up with this. Like, they had to pull an actual engineer to talk about this. So what you have here is 2 sets of force applicators, okay? And the idea is they're applying force evenly to the bottom of these wings, and because they're applying the forces evenly, it's simulating actual flight through air. Because what do we know about air pressure? Well, if air pressure is on one side of the fin or the wing, it will apply evenly to that surface, right? You'll have an even amount of lift that's being generated on that surface. Then, because of flutter, that resistance will be eliminated a little bit. And so what he's done is he has specially tailored his stress amplitude, his maximum amplitude, and minimum amplitude to mimic the realism of flight. Okay, so just a very cool movie. That's why I like to, every time I talk about fatigue failure, I always love to stop and take a look at this movie, because it's a really phenomenal movie. I highly recommend it. Jimmy Stewart's a good actor, and that is 1951's No Highway in the Sky. Okay, so how can we improve fatigue life? So some things that we can do. First, we can reduce the magnitude of our mean stress. That's the easiest way, right? We come back up here and we say our magnitude of the mean stress is going to be somewhere in our safe region, right? So we can reduce that magnitude. And so this failure curve is near 0, or with a compressive mean stress. With a moderate tensile mean stress, that failure curve goes lower here, and then with a larger tensile stress, it's all the way here at the bottom. Which means that your stress amplitude has to drop even farther below for us to exist in this range, right? So if we're up here, if we're near a 0 stress amplitude, then we're actually getting into like kind of a safer region, because we can exist in this range, right? It's kind of hard to see with this graph. But basically, the idea is just stick below your stress of fatigue failure, right? Or your stress amplitude that will be above fatigue failure. Also, if you're in this curve, if you're for aluminum, by lowering your stress amplitude, you actually give it a longer period of time before failure will occur. Even though it will someday, you're giving it a much longer period of time. Imagine if you're working on bicycle spokes, you might not ever, like, something will fail first but before the bicycle spokes fail if they have 1 billion cycles before failure, right? So the second strategy we can use is surface treatments. We can actually impose compressive surface stresses, these are called residual stresses, onto the surface of a material to increase the surface hardness, okay? What this does is actually suppresses surface cracks from growing. So if we have a crack on the top, if we put that into a compressive mode, it's trying to squeeze together the cracks instead of allowing them to open up. You have 2 main methods of doing this. One is called shot peening. And I don't know if you've ever seen a shot peen before, but it looks like a hammer. And the hammer has a rounded edge, okay? And all you do is you take a you take a piece of metal and you just tap it with the shot peening, and you create little indentations, and that little tiny indentation will create the kind of compressive stresses we're looking for. Okay, that's one very practical thing that you can do easily, right? You just buy a little hammer and you hit it enough times, and it'll create this nice kind of. You can tell shot peened materials when you see them. Okay, and then also the second method is actually carburization, and we've talked about that before. I've shown you a gear that has been carburized, and we saw the cross section of it. We talked about diffusion, right, and how you can use diffusion to create different material properties, or cause it to occur in any case. But yeah, you carburize carbon-rich gas into a piece of material, especially steel. And that will actually create a layer, a surface layer that is much harder than the inside of the material. And that will help keep cracks from forming on the outer edge, right? Finally, we can use design changes to increase our fatigue life. And, you know, mainly what we're talking about when we say design changes is we remove stress concentrations, right? You could actually like make your material thicker. That will improve your fatigue life. So if you have, like this width here, if you increase that, that lowers the stress on the material because it's thicker now. It has a larger area across which the stress acts. So you lower your stress amplitude that way. But also if you have obvious stress concentrations to deal with them. Don't allow these sharp edges to exist. Instead, design them with little fillets in mind, and that will actually much improve your system as far as fatigue life is concerned, and also just generally. It's just general good practice among all engineers that you never leave sharp corners like this. Of course, we're not talking about these outer sharp corners like here. We're talking about the inner ones where they connect to other material. Okay, so that is fatigue failure. So now we're going to move into creep. Okay. What is creep? I've mentioned it several times without ever explaining it. At the University of South Carolina, there's actually a whole creep lab that I know of that they study creep, and that's all they study. It's a very interesting problem to have. But basically, if you put a material under a constant stress, okay, so instead of our fatigue failure where we have like an oscillating stress, we now have a constant stress level. If we put our material under a constant stress, and usually if we apply a little heat as well, or enough heat, your material will actually and I'm saying a really long period of time, your material will slowly, ever so slowly, stretch and stretch and stretch and stretch and stretch before it actually finally ruptures, okay? So these are subdivided. These regions are subdivided into three different regions. You have primary stress, which is like the initial onset of creep. You have secondary stress, which is also referred to sometimes as steady state stress. Steady state creep. Sorry, where you have a linear curve that actually aligns with your strain to time, okay? And then finally you have tertiary stress, where you actually have necking beginning to occur, okay? So it's a lot like a tensile test, except it's happening below your yield stress and over a really long period of time, okay? This could be years, right? This occurs at elevated temperatures for most metals. So usually if your metal is at 0.4 of the melting temperature, you will have creep happening. So like if you think about steel buildings like skyscrapers, are those at 0.4 times the melting temperature? No, they're probably like at room temperature. Even if like they're really hot, right? They're probably not at 0.4 the melting temperature. But what about aircraft components, like in the jet engine, where you have really high temperatures in certain places? Well, then it can definitely happen, right? And again, the higher that temperature is and the higher the stress is, you're actually going to increase or decrease the amount of time needed for creep rupture to occur, okay? And also, creep can then contribute, because remember, true stress exists, so creep can actually contribute to premature failure of your material. It doesn't actually have to creep all the way to the end. It can actually just contribute. So, again, we've got primary, secondary, and tertiary, and yeah, and we have an acceleration of the rate of creep here towards the end before it ruptures. It's kind of like necking. Okay, so here's just an idea of what happens when we're creeping at different temperatures. So at less than 0.4 times the melting temperature, we don't have creep occurring. We just have elastic deformation, if any, right? Then as we grow in temperature, we then have a higher curve that has a shorter time frame, below infinity. Then as we increase the temperature more, and actually it's temperature or stress actually. As we increase the temperature or stress more, this curve gets steeper and we rupture faster. And then again, even steeper and faster in the highest temperature or stress scenario. Steady state creep rate, or sigma dot S, okay, which is steady state with subscript steady state, sigma being strain, and then the dot being rate, so steady state creep rate is what we're looking at, increases with increasing temperature and stress. The rupture lifetime, TR, and let me come back to here, TR here, that's that rupture lifetime, will decrease with increasing temperature and stress. Okay, so what I have here is an equation for steady state creep rate. It is equal to a material constant, K2, multiplied by our stress to the power of n. That power of n is called a stress exponent, which is a material parameter, multiplied by the exponent of negative QC, which we've seen something very similar to this actually before. Which is QC is here the activation energy for creep, which is a material parameter, divided by RT, where R is our gas constant. Okay, and so so our steady state creep rate is constant actually for constant temperature and stress, and so strain hardening is balanced by recovery, and there's a dependence of steady state creep rate on our temperature and stress. So we've already covered these things. Okay, there's a lot on this slide, so I apologize for the kind of confusion. The biggest thing to take away from this is this equation, because it will help you calculate what the steady state creep rate is. And basically what that means, like what does that even mean? Well, steady state creep rate is just how long does it take for it to slowly stretch over time. Like in 45 days, we might have gone from here to there, right? Okay. Okay, so we can also predict, and this is very important for engineers' purposes, but we can predict the creep rupture lifetime, okay? So that time to rupture TR, we want to know when that is, right? Because we don't want somebody to be flying on this plane when that happens, right? So creep data for a prolonged period of time is impractical to collect in the lab. So we can actually extrapolate it from data collected for a shorter time at higher temperature. So that's what the lab at USC that I was talking about does. They actually put objects under stress in a giant heated chamber, and that actually causes this creep to occur at a faster rate. But you can use the Larson-Miller parameter M to actually adjust the temperature that you're looking at now to the temperature that you expect it to actually be at. And that is your temperature multiplied by a constant, normally approximately equal to 20. So this could be a material-dependent constant. There's a lot of these kind of just arbitrary material-dependent constants that you have to deal with. Plus the logarithm of time to failure, or log of time to failure. And that is all equal to our M, okay? So what we do is we start with some temperature. Let's say I know temperature 1 and I know the time to failure. for 1, that is equal to some m, all right? The Larson-Miller parameter. And then I say, okay, at the temperature I'm actually going to use this at, I know m already. What is TR, right? And then based on the material I'm talking about, I choose C. Okay, so here's an example. We're going to estimate the rupture time TR for an S590 iron at temperatures equal to 800 degrees Celsius. And sigma, this little weird squiggly thing is another way to write sigma, I guess. I don't like it. But stress is equal to 20,000 PSI, okay? So how do we find this? Well, we can actually plot our log of stress versus the Larson-Miller parameter for this material. That's the data for S590 iron. We know our stress level. And so we come over here and we draw a straight line from 20 times 10 to the 3 PSI, which is 20,000 PSI. We hit this and we draw straight down. And this is on a 10 to the 3 meter Kelvin hour range. And we plug 24 times 10 to the 3 into our Larson-Miller parameter system. So for most materials, we actually have Larson-Miller parameter at whatever stress level we need. And then we know temperature, okay? It's 800 degrees Celsius, so we put 1073 in here like in this position. Why is that? Well, because Kelvin is 273 plus whatever your Celsius temperature is. 800 plus 273 equals 1073 Kelvin. Then we choose 20 for our constant, and then plus the logarithm of TR. And then if we solve for this TR, we get 233 hours, okay? Okay, and I moved through that really quickly, so if you have questions about this, please let me know. Feel free to ask, and I'm always happy to make time to answer specific questions. Don't feel sheepish about asking, so. All right, thank you for listening.